Okay, so PD11. So this is one of these physics equations that can be discussed knowing partial derivatives. And by the way, there is a field of math called partial differential equations. And I think you guys have probably heard of differential equations. In fact, in Math 32, you actually do a little bit of differential equations. You talk about the natural growth equation, and those are differential equations because they involve derivatives, right? This is called a partial differential equation because it involves partial derivatives. And it turns out that partial differential equations relate to the real physical world in extremely cool ways. This is just one of them. And then these other applications earlier, there's the heat equation and Laplace's equation, et cetera. And these are also relate to the real physical world in important ways. So this is just one example. And here we go. So the equation that we're interested in, the equation that we're interested in is this. So second partial u with respect to t minus c squared second partial u with respect to x equals 0. Okay. So any function u of position and time that satisfies this equation, I claim, is what we call a wave. And let's talk about, what does that mean? So y'all have seen waves, of course. That's not news. And this is a one-dimensional wave because there's only one position variable. So I call this a wave because if you think about what a wave does, right? A wave is, if you were to take a photograph of a wave, then it's like it's go up and down or something like that. And it's got, the height depends on position. Right? But it also depends on time. Let me draw sort of a picture here. You might have a little tank here, let's say, and you might have a wave that momentarily looks like that. But, so, height will depend on position. But sometime later, the wave might have changed. It might have moved over a little bit. So at some later time, there's a different height for that position. So it depends on both position and time. Everybody see what's going on there? So this kind of a function is an attempt to represent a moving wave. So okay, so they give us the following. I say they. So I've given you a particular function. W of x comma t is f of x minus ct. Now, importantly, this is a function from R2 to R1. This is a function that has two variables, two input variables, x and t. Right? Who asked me this question? I forgot already. Yeah, okay, right. Okay, so two input variables. This function here only has one input variable. This is just a single variable function because a single number, that single number being x minus ct, is what goes into here, and out comes a value, f. Okay. All right. So if I want to know if this function w satisfies this equation, what I've got to do is start computing, and let's check. Is it the case that the second partial of w with respect to t squared minus c squared second partial of w with respect to x squared, is that equal to 0? So we calculate as follows. First, let's compute the second partial of w with respect to t squared. Well, that's the t partial of the partial of w with respect to t, and that is, let's see here, the t partial of, I need to compute now here the t partial of this function. So in other words, I'm going to take the derivative with respect to t of this expression. Okay, so partial with respect to t of f of x minus ct. All right, and I claim that we've got a little chain rule problem here, kind of, a single variable chain rule problem, because the thing I'm interested in is a function of x minus ct, x minus ct is a function of t. So altogether what this gives me is I'm going to be taking f prime of x minus ct, and now I've got to multiply by the derivative of x minus ct with respect to t. Does that make sense? So that's times negative c. Okay, so let me pause on that for a second. Does anybody have any questions about that? Is that good? Okay. Okay. All right, so now let's do the next t derivative. And I claim it's kind of similar. I'm still taking the derivative of some expression involving x minus ct. Now I've got this extra factor here that's going to just sit there. But nevertheless, when I take the derivative with respect to t of this expression, first I take the derivative of the outside function. And then I've got to multiply by the derivative of x minus ct with respect to t. And that's another factor of negative c. How are we doing? Okay? All right. So altogether that gives me c squared f double prime x minus ct. All right, now next I need to, so I've computed this term here. Next thing I need to do is compute that term. So I need to compute second partial w with respect to x. Well, that's the x partial of partial with respect to x of x, f of x minus ct. Same deal. I mean, again, this is a chain rule kind of thing. This time, though, when I take the derivative with respect to x, yeah, it's a chain rule, but I end up, instead of getting an extra factor of minus c, I'm going to be getting a factor of what is the derivative of x minus ct with respect to x. And that's just an extra factor of 1. So I claim what we're going to get is f double prime x minus ct times 1 squared. Oops, there we go. Cool. So now taking these two results, plugging into this expression here, I'm going to take this one, and then I'm going to subtract c squared times that one. And I claim that, yeah, when you take this and multiply by c squared, it's exactly the same as that, and when you subtract, you do get 0. So check. That make sense to everybody? Is that cool? Everybody else okay? Okay. All right, so what I want to do now is I want to, so the second part of the problem says use the ideas of translation from section 2.2 and let's determine the velocity of this wave. So in other words, forget about the differential equation. Let's just look at this expression and let's see, can we make sense out of, in what way does this actually, why does this represent a wave? And here's the idea there. I claim that, let's talk about the graph. Well, gosh, let's see here. Sure, let's look at the graph of f of x minus ct. So let's look, in other words, let's look at z equals f of x minus ct. And let's do this at a couple of different times. So for example, let's look at t equals 0. Well, at t equals 0, we're going to have some, I don't know, some curve here, whatever. Let's say it's a wave that looks kind of like this. Let's say that this is z equals f of x minus 0. I'll just say minus 0. So in other words, this is just z equals f of x. On the other hand, what happens at some other time, let's just say t? Well, there's going to be some picture here, and it's going to, the equation for this graph is going to be z equals f of x minus ct. What's the relationship between these two equations? The relationship is that this is what you get when you replace, in this original equation, when you replace every x that you see here with x minus ct. So x got replaced with x minus ct. So the punchline is this picture is going to look a lot like this picture, but it's just been shifted over by a distance of ct. Oh, that was terrible. This is supposed to be pointy like the other one. Sorry. So this has been shifted over, and that distance is ct. Is everybody with me on that? Okay. So what that means is that in an amount of time t, this picture, this wave, has slid over to the right by a distance of ct, and so the speed, being distance divided by time, well, in this amount of time, t, it's moved a distance of ct, and so the speed is c. Does that make sense to everybody? Everybody see the speed is c? In particular, it's a speed c in the, moving to the right. It's, it's moving that way. So, if you look back at the original differential equation, now the original partial differential equation, we call them PDEs, by the way. So the original PDE is that, again, second derivative of u with respect to t minus c squared, second derivative with respect to x equals 0. In this equation, that number, c, that little number c there, that's the speed of the wave. And that's something that you can recognize inside of the equation, inside of this what we call the wave equation. The thing that gets squared at this point in this equation, that thing that gets squared, that's the speed. Okay? Questions about this? So by the way, at some point you guys might take a class in signals or something along those lines, and I honestly, I've never had such a class, but I've had physics classes that are comparable. I was a physics major in college. You're probably going to see equations kind of like this that describe waves moving through any type of wave, really. Okay. All right. Any other questions about this problem? Okay. Let me stop this recording.